Well, hi, everyone. Welcome to this brief introduction and overview to the Metalog distributions. The Metalogs were developed for a very practical purpose. That is, to have a set of continuous probability distributions that are more flexible and much easier to use than the totality of the previously defined classical distributions. You can see here lots of thoughtful people are saying good things about the Metalogs, but let's get on and see what we can use them for and what some of their limitations are. The Metalog distributions are an alternative to classical distributions, or they can be thought about that way. Wikipedia lists about 115 named continuous classical distributions, many of which you're familiar with. The Metalogs expand this list by an additional 60 practical distributions, expanding the list by more than 50%. And the purpose of this quick introduction is to help you decide whether you'd like to add Metalogs to your toolbox. Metalogs are likely to be your best starting point for fitting continuous distributions to data. It could be expert assessed data, which such as you want a continuous distribution to run through 3 expert assessed data points. It could be simulation data, where you want a closed form probability distribution to represent the results of a simulation, and to do this far more accurately than would typically be possible using classical distributions. It may be empirical data. It may even be multimodal, as in this example here, where once again, the Metalogs will fit the data better and more easily than classical distributions. So why is that the case? Well, it's because of the properties of the Metalog. One is that they have virtually unlimited shape flexibility. They can emulate virtually any distribution or data shape. Secondly, you can fit them to data so simply with ordinary least squares. There's no nonlinear optimization required. Third, you have a choice of boundedness. Fourth, you have simple closed form equations, both for the quantile function, that is the inverse CDF, as well as closed form equation for the PDF. And finally, given that it's a closed form quantile function, you have it's very easy to simulate in closed form for further analysis. So this means that the Metalogs, which were originally developed for the field of decision analysis, they actually have virtually unlimited applicability in any field of human endeavor. So what is a Metalog? Well, we start with the logistic distribution, and here is the CDF and the PDF of the logistic distribution, which looks a lot like the normal. It's just slightly narrower and has slightly heavier tails. But nicely, it is characterized by this beautifully simple closed form equation. And the curve on the left, the CDF, is now expressed as a quantile function, where we have x as a function of cumulative probability y rather than the other way around. But look how simple it is. The mu is the mean. The S is usually a constant, like a proportional to the standard deviation. This is the beginning of the Metalog. And here we modify the logistic distribution by asking the question, what if S, this the spread parameter, smoothly increases from right to left? Well, that thought experiment leads one to think that you might get a right-skewed distribution. And here I've modeled S as just a simple linear function of cumulative probability y. And by doing that, we have all these shapes available to us. This is, in fact, the 3-term Metalog distribution. We can do the same thing with mu. We can ask, what if mu smoothly increases from left to right? Well, if it does, and if we use the same sort of linear equation with a different set of constants associated with it, we get all of these shapes, all the way from uniform up to something that's very, very peaked with very fat tails. Well, that's the 4-term Metalog distribution, where A2, where A3 is actually 0 for these illustrations, but you can do all combinations. Why stop there? Why not, if we're going to do that, why not expand S as a whole power series with any number of terms, and the same thing with mu? And what you see here is the definition of the basic Metalog equation. Metalog is short for metalogistic, meaning a generalized form of the logistic distribution. If we just simply plug in mu and S from these equations, we end up with as many terms as we want in a Metalog distribution. And like a Taylor series, it can have any number of terms. You can see the 2-term Metalog quantile function all the way up through the 10-term Metalog quantile function on this graph. Each additional term defines a different probability distribution, number one, but most importantly, each additional term adds shape flexibility. So you have the flexibility to have as much shape flexibility as you want. And I'll show you 4 choices of boundedness, 15 distributions within each choice, roughly 60 practical distributions in the Metalog family. So every Metalog consists of 2 simple closed form equations. The first is the quantile function that I just showed you. I'm using here as an example the 3-term Metalog quantile function, but this is true for any number of terms. If you simply differentiate that equation with respect to cumulative probability y, you get dx dy. And then if you take the reciprocal of that quantity, you've got the dy dx, which is by definition the probability density function, PDF. And so every Metalog distribution not only has a closed form quantile function, but also a closed form PDF that's a function of cumulative probability y. So where do we get the coefficients from? These determine the shape of the Metalog. Well, if you start with the quantile function, and if you start with some points on a graph, such as here, we have data. We have 10, 50, and 90 on the y-axis associated with x values 40, 50, and 60. Well, according to the Metalog equation, if you just plug in those values, you'll have 3 equations and 3 unknowns, which uniquely define the A coefficients just based on that data. And the equation is simply the vector of A coefficients equals y to the minus 1x, where y is the matrix you see there. And so the A coefficients are simply determined from this linear calculation. What if you have more data and you want a smooth curve to go through lots of data, as shown here now on the graph? Well, this formulation simply generalizes to the ordinary least squares equation, multiple linear regression, if there are more data than terms. And this is a nice closed form way of getting to a curve that goes through your data, minimizing the sum of squares. And from a statistics perspective, this actually, if you assume the standard Gaussian noise assumptions, this is actually the maximum likelihood estimate for the AI coefficients. Now, there are some limitations and considerations with ordinary least squares. Here I'm showing 6 points that may have been assessed from an expert and a 4-term Metalog going through those. Looks like quite a good fit. What if you used a 6-term Metalog? Well, the good news is you'd go through every one of those points exactly, but the bad news is what you have left is not actually a valid CDF. That's what we call infeasible. So you don't want to, it's important not to overfit or use more terms than you should be using with Metalogs. A second is overfitting and underfitting. So for example, I have some data here from an actual decision, a real world simulation, a decision analysis. 2-term Metalog doesn't fit that data very well. A 5-term Metalog fits it beautifully. If I use a 16-term Metalog, I'll get some wavy shapes on the PDF here that are not actually characteristics, that they're more amplifying the noise rather than amplifying the signal. So there's some judgment involved in determining which Metalog you'd want to use. In this case, I'd certainly use the 5-term Metalog. So there's always a feasibility requirement that the density function has to be strictly positive, and that generally needs to be checked. There are various alternatives to ensuring feasibility. One is to determine the AIs as a linear program, and there are published papers on that. But I simply like to just plot the Metalogs for the various numbers of terms and see what actually looks best or seems best for the data I have. So there are various alternatives for dealing with overfitting, but also, again, visual inspection is often my preference. Now, I said that you have a choice of boundedness. The equations I showed you previously are for the unbounded Metalog distribution, and that's the quantile function that I showed previously that can have any number of terms. Well, just like a normal distribution, if you say the log of a variable is normally distributed, then that variable itself is log normally distributed. The same is actually true with the Metalog. If a log of a variable is Metalog distributed, then the variable itself is is log Metalog distributed, which is what we call the semi-bounded Metalog. It has a nice closed form equation, and it can be fit to data in the simple ordinary least squares way, just like the unbounded Metalog, but this one, of course, has a lower bound that you can specify. And similarly, if you say that the logit of the random variable x is Metalog distributed, now you end up with a nice closed form equation, same ability to fit to least squares, but now this has upper bounds and lower bounds that are strictly honored, just like the beta distribution would. So we have choice of boundedness built in. There are moments available for the Metalog distribution in terms of the A coefficients. And you can see here that here's the mean, variance, skewness, and kurtosis of the 5-term Metalog distribution. These are, as you can see, polynomial functions of the A coefficients. And in fact, unbounded Metalogs have an infinite number of finite moments in closed form. You can get these moments for up to 10 terms. They're published on the website metalogs.org. Moments of semi-bounded and bounded Metalogs are not available, it turns out, in closed form. So now let's turn to shape flexibility. We said that the Metalogs have virtually infinite shape flexibility. Let's take a look. Let's suppose we we parameterize a Metalog with data from a standard normal distribution. There's 105 points off the normal distribution. We fit a Metalog with that. If it's a 2-term Metalog, it's not that great a fit. A 4-term looks awfully good. 6-term Metalog fit to that data by least squares, looks great. 8, 10. Goodness, you can't see the difference. What about the density function? Well, there's the 2-term Metalog density, 4, 6, 8, 10. So basically, by the time you get to 10 terms, there's a Metalog here that virtually identically approximates a normal distribution in a way that it's almost impossible to see the difference visually. What about a log normal distribution? Well, if we took 105 points off a log normal distribution, use those to parameterize a 2-term Metalog, that's what you get, 4, 6, 8, 10. Once again, nearly identical. What about a U-shaped beta distribution approximated with a logit or a bounded Metalog? Well, you'd think that would be pretty difficult. No, not at all. There's the 2-term, 4, 6, 8, 10. So once again, the Metalog can approximate virtually all beta distributions exactly, but yet it has far more shape flexibility than the beta family does. How well does a Metalog do in representing Weibull distributions? Well, here are Weibull distributions with various numbers of parameters, the various shape parameters, and the Weibull PDFs in blue are the exact Weibull, and the dashed yellow curves are the Metalog representation. This is a 9-term log Metalog. It goes exactly through each of these 9 points you see on the right. So this is a special case of a far more general result, and that is that any probability distribution with a continuous quantile function can be approximated arbitrarily closely by a Metalog. What's the proof of that? Well, any continuous function can be approximated arbitrarily closely by a polynomial. That's the Weierstrass approximation theorem. The Metalog contains a polynomial, so if you set the non-polynomial terms to 0, you've got something that will approximate any quantile function arbitrarily closely. So, set of observations that goes along with this, a single set of Metalog equations can represent any distribution. Potentially obsolete questions. What probability distribution is best for this application? How do we fit our data to that probability distribution? You don't have to ask that anymore because you already have a distribution that's more flexible than any classical distribution you choose. There are some practical limitations in the Metalog world, distributions with spikes, discontinuities, and or extremely fat tails, and I'll show you some of those in a moment. So let's talk about empirical data. Here's an example from fish biology where I gathered 3,474 weight samples of steelhead trout from the Babine River in British Columbia. And there's a big steelhead trout there. That one weighs about 20 pounds. But out of these samples, you see these fish weighed anything from 5 to 25 or 30 pounds. And if you tried to fit that with a log normal, then of course you get something that has a log normal shape. But if you fit it with a log Metalog, which is a better representation, you'd probably get a better shape. One of the things that we have always wondered about steelhead is what happens. Steelhead are born in the river, they go to the ocean, they fatten up for a few years, they come back, and when they spawn, For the first time, they're called one salt fish. When they go back to the ocean for a few more years, come back up again to spawn again, they're called two salt fish. Fish biologists really have no idea, or at least not until this research, what are the relative fish weights of one salt versus two salt fish. That is, how much time do they gain in the ocean? The reason you can't tell that is because all the steelhead look the same once they're back in the river. But interestingly enough, the Metalog, and here's the histogram of the 3,000 data samples. The Metalog, if you go with the you're seeing here is the log normal, but if you go with the two-term Metalog, it's pretty similar: 4, 6, 8, 10. By the time you get to 10 terms, look at this. The Metalog has picked up that there's actually a bimodal shape in this data. And could that be the explanation for one salt versus two salt fish? The younger ones are the lower peak, and the larger ones are the upper peak, or at least very likely so. How many terms should we use? We often use a Metalog panel to help address this question. The Metalog panel arrays the Metalogs on the same set of data from 2 to 16 or however many terms. This is a different example, quarterly returns on investing in gold. But you can see here, for example, that some are bimodal, some are unimodal. The bimodal ones probably have an explanation, just like the fish did. Some of these may be overfit. The blank ones may be infeasible. But the Metalog panel will often help you quickly zero in on the number of terms you'd like to use. So Metalogs are smooth and continuous, and the limitation is that distributions with gaps, if there's a big vertical jump in the CDF, Metalogs probably don't work so well. If there's a big horizontal jump or horizontal space, that is, you've got separated PDFs, Metalogs probably don't work very well. But other than that, there aren't many limitations. There's a Metalog that works well for virtually any practical data set. So the Metalog family of distributions is quite unique. It embodies all of these following desirable properties, and it's these 5 properties together that constitute comprise the uniqueness of the Metalog distributions. And in terms of resources, there are free publications. There's a Wikipedia article, but look at the Metalog distributions website. It's got a full set of publications. There's free software there. If you want to compare Metalogs to conventional distributions, Analytic Solver by Frontline Systems fits both Metalog and classical distributions according to any set of data, and uses user-selected goodness of fit criteria, so you can experiment around with both. In any case, that's the quick summary and overview. Get in contact with me if you have any questions, or just go to the website of the Wikipedia article. You find plenty of additional information. Thanks very much for your attention. Have a great day.